All right, so we're here today. My name is Chris. I'm the managing director of Diagno, and we just decided that it would be good to do a recap of our Race 2030 project that is nearing completion, not quite complete, but nearing completion. And so here with the researchers that have brilliantly been helping us through the project, and Earl, who's the CTO of Diagno. And yeah, maybe you could do an intro of who you are and what you do.
Thanks, Chris. My name is Bernardo, and I'm a researcher at the Institute for Sustainable Futures here at UTS. And I mainly work with data science, often applied to either energy systems or we call it resource systems, but more specifically looking at decentralized energy resources like PV systems, batteries, vehicles connected to the grid, and etc.
I'm Jacques Rougier. I'm an associate professor at UNSW, and I am leading the project on the UNSW side, working, on the PV side from, the entire value chain, from, technology to systems, and more recently with you guys a lot on operation and maintenance and how we're going to maintain this exponentially growing fleet of PV in Australia.
Yeah, absolutely. Earl?
And hi, I'm Earl Duran. I'm the CTO at Diagno Energy. I oversee the operations and the development of the platform. We've been running this business for about 3.5 years now. And yes, excited to be here today.
Yeah, awesome. Before we jump into the details of the project, I was hoping, Earl, you could give us sort of an overview of what the project is and more importantly, why it matters.
Yes, so this project is part of the Race for 2030 initiative. It's a 1.5 year project split in 6 work packages. And the idea, the broad initiative of this Race for 2030 grant is to, create solutions that help meet the net zero targets. And so what we have proposed and wanted to collaborate on with UNSW and UTS is to improve the sort of the detection and the diagnostics of faults and issues in solar and battery assets. And so, yeah, we'll go into details of those, but yeah, they range from looking at very specific issues about the generation themselves at site level to all the way to looking at calculated performance anywhere in the world and looking at the asset within the network, not just as a single asset, but as a part of a network of assets. And so this obviously matters because there is a huge issue at the moment with the ongoing oversight and maintenance of assets. So the challenge in the current mindsets is about deploying at scale, and that's great. There's a race to deploy these renewable assets, and that's very important. But no one's really thinking about how to maintain those assets, make sure that they perform reliably over time and safely. And so this project was to support that, to help the industry be better at maintaining these assets over time.
Yeah, from my experience, one of the things I've been doing is going around the country as part of a couple different road shows and asking installers and retailers and EPCs if any of them offer a formalized O&M service with SLAs, and almost exclusively the answer is no, because they are too busy installing and they don't have time to follow up on the work and maintain it, and they don't know how to turn that into a money-making endeavor for themselves. So this problem is real and growing. And I guess one of the things I want to ask you is, are you able to give us some scale to this issue? Like, can you put some numbers behind some of the things that we found?
Yeah, of course. So currently we have about over 6,000 assets monitored, and from those assets, we've run some analysis on things like performance, generation loss, number of issues, etc. And we find that looking at those assets across Australia, on average, we identified about 250 kilowatt hour per kilowatt peak per year of generation loss for solar generation assets. And that's about 12 to 16% of generation loss for those assets, which is huge. especially when you look at large commercial industrial assets. That's a huge loss, and that's just the average. When you look at the long tail things, you see things that are really a lot worse than that. And so this is obviously a very big number. When we extrapolate that to our portfolio and we calculate a savings loss by virtue of not generating, and what is the savings loss associated with it, we found about $9 million of savings loss with a portfolio of about 300 megawatt peak. Extrapolated to Australia, which is, I forgot the total, it's that's global.
It's about 40 gigawatts.
40 gigawatts, that's right, 40 gigawatts of solar in Australia. That's about $1.2 billion of savings loss by virtue of not generating what's expected. And so these are huge numbers. And then when we extrapolate even further globally to 2 terawatt, that's more around a $60 billion loss. So there is a huge market opportunity there. Again, that's a problem that is invisible. That's not something that we see and feel every day, but it is very much there. And so, just want to give an idea.
And those are the numbers today. Globally, we've got 10x the market, if not 100x the market. Yeah, so one thing that we found with working with the customers that own this 300 megawatt portfolio fleet that we're looking after is that a lot of them offer performance guarantees. Either they're an EPC or they are a solar retailer or an installer, and they offer performance guarantees to their customer. And this is actually a really difficult thing for them to do accurately. A few groups offer a performance guarantee in different ways. There's different contracts, and they've got different ways of tracking it, managing it. And by and large, the customer has to trust the EPC that they are tracking it accurately, because they don't have a way to assure the performance guarantee. So one of the work packages we put together was dynamic rebaselining, and that's something that you looked after during the research project. And I guess I was wondering how you guys went about picking apart the different aspects of a performance baseline that affect performance, clipping, shading, faults, other forms of tripping, so that you could put them in specific buckets reliably. Like how did you go about that process?
Yeah, no, that's a really good question. And look, when we first started in this topic, is we looked at the literature first to see what's out there, and what we see is that the focus is primarily on the system itself, right? On the DC side, on the faults, on the system side, and it's very academic. And so one of the things that really sort of surprised us was that internationally the literature doesn't really look at the grid impact on the system itself. And in Australia, it has a dramatic impact, as we know, with the really heavy penetration of PV. And so that's why we have clipping, and we have tripping due to over voltage on a low voltage network, and those sort of things. And so for us, that was really about looking at those time series, right? So what we're doing here is we have a lot of time series from inverter data, and looking at this time series, but not just from physics point of view, but also it's about understanding the standards, the inverter standard for 3.7, understanding how the DNSP operate, understanding the different region in Australia, and understanding how does that impact the operation of the system. So I think the great thing about this team that we have is that we have the different competence, right? We have the understanding of the physics of the system, understanding the engineering, the design, understanding the standards, understanding the interaction with the grid, and also with the AI and machine learning expertise. And I think you need all of this because it's actually extremely complex. So yes, after we've identified the main buckets, and that was really a collaboration between the universities and you, sort of tripping, clipping, shading, zero generation, and all these other things. It's about finding features that allow us to determine how we can detect them automatically, and it's not necessarily there's one and there's the other. It can be multiple at the same time. You can have a clipping, which is, it looks like a flat line like this, and then in the middle of that clipping you can have a tripping, and then it'll go back up. And the going back up, it has to be over 6 minutes because that's what the standard says, right? So you need to understand the standards to understand how to design the algorithm, to understand how to detect those things. And I guess that's where the richness of that project comes from. We are not just machine learning or AI expert who just go in there and try to get features and getting a black box to spit something else. We go in there, we try to understand what's the physics, what's the standard, what's the interaction with the grid, and that's how we design this system. So it's really a lot more details than it can be from the outside. Yeah.
Yeah, one thing I really loved about these projects is that we are going like way down into the weeds and figuring out, like you just said, if it's clipping and tripping, like how do we parse that apart? How do we understand the physics and the standards, and how does that materialize in the data that we see? So like a rich information and research that's been done, and all that boils up to making sure that for us, what that boils up to is making sure that an EPC or a retailer can accurately guarantee performance to a customer, because that's something that it sounds really simple, but it's just not happening in the way you'd expect it to in the market.
Absolutely.
So I think it's super important, and the work that you get. And going back to one of the things you started by saying is, yeah, this team is absolutely brilliant. Like I just think we've worked incredibly well together. This is our second of hopefully many projects together, and yeah, UTS and UNSW and Diagno have really enjoyed working together. Yeah.
Yes, we same here.
Yeah. Bernardo, I wanted to ask you, one of the things that we've been doing at Diagno is looking at the faults and issues of a specific system. But as our portfolio grows, we can leverage information across sites and areas of the network, and maybe in the future even countries, to get information that can help us to contextualize specific fault data or specific events that are happening at a site. So one of the things that you worked on was looking at what happens at a network level. And this actually turned into a project with AIMO. And one of the things I was thinking about when you were doing this project is actually the Iberian blackout of 2025. Because that started with some grid oscillations, and they had a large amount of solar and wind on the network at the time. There wasn't a lot of inertia. Their network is a bit different to ours, but it tripped. It ended up with a cascading fault and lost the entire grid in Spain and Portugal. And when AIMO engaged us to get involved with this part of the project, I was thinking maybe that's sort of where they were headed, because they had no great oversight, in particular with commercial and industrial systems, solar systems in Australia. I think at the time they only had a couple that they had oversight of, whereas Diagno have a few thousand. So I was hoping you could tell us a little bit about this project and what you discovered when they gave you some network faults to look into, and what sort of correlations you were seeing across the Diagno fleet.
That is such an interesting question. There's a lot to unpack there. But I think the best way to start is to look at the grid as a giant machine, right? And then you have this huge machine that's been operated and maintained for many decades now. But with the opening of the market to individual users like ourselves, or even industries, but individual users, we start to see some challenges that we hadn't seen before that the infrastructure have to adapt to. And Australia is doing an amazing job with solar penetration, and I think Australia is the test bed of the world to understand how this implementation and penetration of solar and wind and batteries and vehicle to grid will affect that huge machine in different places. And when you look at this machine from a urban fabric, let's say Melbourne or Sydney, or even a small country like the Netherlands or Belgium, or a large country for that matter, you can start to see how the penetration of solar does affect points of the grid. So if you have a street or a certain neighborhood with a high penetration of solar, and they're all feeding back energy into that machine at midday or 1 p.m., you might see changes in voltage in the grid. And in Australia, we have standards that protect the grid. So if the voltage goes above or below a certain threshold, the inverters, smart inverters in that case, that have been installed after a certain date, will have to respond to that kind of phenomena. And they might respond by reducing the generation for some time. They might respond by tripping completely, waiting some time and reconnecting after a few minutes, but they do respond. So at the end of the day, that's a signal that we can pick up individually, but it's also a signal that we can pick up as an aggregate of inverter brands, and that by itself already can give us a lot of intelligence. But more importantly, through an institution like Diagno that aggregates a lot of different inverter brands, we can pick up a amalgamation of all of these different sensors within a geographic location. And that by itself can gives us so much understanding of what's happening. So when we look through the lenses of a grid event, like for example, in a couple of years ago in, I think, Moranbah in Victoria, transmission lines fell down because of a storm or something like that, and that repercuted down the grid. And a lot of inverters disconnect in response to that particular event. So when you look at the data from one side, you would see generation going up as the sun rises, but then at some point the inverter would disconnect completely, come back to generate and keep going. If you are the asset manager and you see that trip, you might not even care. I mean, if just trip for a few minutes, that's okay, it happens, you might not dig deeper. If you are an asset manager that has a few sites in the same place, you might find it curious. But if you have the capability of looking at 3,000 sites and you see that 100 sites around a certain geographical location trip, I mean, virtually at the same time, that might indicate that something happened, right? So in one hand, that's powerful to whoever would benefit from overseeing that event happening almost in real time or with a 5-minute delay or something like that, depending on how the data is aggregated. But it's also beneficial to understand how that can indicate that something happened. So that might support first responders in a way, but it can also help us understand the way in which all of the systems are responding to this great event. So it goes both ways. Understanding that the event happened, but also understanding how that responds to the event that happened.
As you're doing your research, do you think that if you had enough sites that you could actually see when that fault happened and pinpoint when and where that fault occurred on the network?
So this is the interesting bit about the work that we've been doing, is that it kind of moves in a spectrum of complete darkness and then you have no idea what's going on, to the first step, which is something happened. So you can look through the performance of a site. And if the site is underperforming, as in it's not hitting the 100% of generation that you expect or close to 100%, it's actually 60%, 50% every day, you know something happened, right? So that's the first indication that something's going on. And then the work we've been doing all together for the past, I think, 2 years, even before the Race for 2030 project, has been step by step kind of increasing the granularity of how we understand how to indicate that something happened, but what happened as well, and to what extent that affects the system, both from a financial standpoint, but also from a maintenance standpoint, or even environmental standpoint, if we're measuring CO2 emissions and etc. But to get back to your question, I think we can get to a certain point, which is we could say that something happened. Why it happened might not be possible, depends on the signals we have. And that's limited by the number of signals that we get. If we only have generation, we can only go as far, but if you have voltage and frequency, we can start to unpack a little bit more, but also the aggregation of that data. So a lot of the data we get from OEMs is sometimes aggregated at a timestamp interval, like 5 minutes or 60 seconds, 1 minute or 10 seconds. And depending on how that is aggregated, that changes the level of how much we can understand about what happened. So I think, yes, we can say that something happened. To answer what happened, why it happened, and what we should do about that, we need a little bit more data than we have right now. And that's, I think a lot of the work we do is also understand where the limitation is, so we can go back to OEMs and go back to industry and really get everyone together in the same room to understand how, if it's an important challenge to solve, which I think it is, and when we have this agreed understanding, we try to move on how do we collect and we make the data available as well. That's the last challenge as well, because each OEM might have a different way of putting the data online, different ways of accessing the data, different time spans in which they keep the data. So if we're looking at an event that happened 1 year ago, we might not be able to query that data anymore. So yes, we can, but right now up to a point. But I do think that we can definitely bring this conversation to the table and get to a point that we will be able to answer these questions.
Yeah. Oh, that'd be super exciting if we could. I'd like to test your memory if I could.
Yeah.
You said something at the beginning that when the system came online matters because they to adhere to different standards. So the 4777 has changed over time, and you have different requirements as we move forward in time. Can you recall from the research that you did if newer installations were able to ride through the fault as opposed to older installations that may have tripped? Which that question is based off an assumption, but can you remember if the inverters that were installed at different times had different reactions to the fault that you were describing?
Yeah, unfortunately, I think we only we collect the data for roughly 3,000 systems. A subset of that in the hundreds were quite useful to the work we've done, but we only had a teeny tiny subset of what I think there's 16 or 18 inverters that we had the commissioning documents, which we could infer the installation date and therefore infer the expected standard, which might or might not be the case. Right? You literally have to go to the inverter to check what the settings are, but assuming that the information we had on the paper was correct, we only had 16 or 18, I can't recall, but less than 20. And I think all of them, if not most of them, were installed after 2020, which didn't give us like a clear kind of break point to compare like previous standards, if that makes sense.
Yeah. So TBC, we need more.
I hope so.
We need more. We need more sites. Well, that's the goal: is to get hundreds, thousands, tens of thousands of sites. Just to talk, continue with you on a related work package. As I recall, the work package that you were just discussing, you actually ended up using fault codes because the timestamps were more specific than the 5-minute time series data that we typically use. We also had another work package that pulled out fault codes and created a single repository of faults that you were mapping against. Our idea was that a Diagno detected fault could be then contextualized with the fault codes from the inverter. Are you able to tell us about that piece of research and how often you found faults that came from the inverter that were real that Diagno didn't pick up, faults that came from Diagno that were real that the inverter didn't pick up, and how often they were correlated in some way? Is there, what did the research reveal?
Yeah, that was actually a super interesting piece of work because when we worked with the power signals and the voltage signals and etc., they're often aggregated at a 5-minute interval. So at any given day you have, what's that, 5 times? How many in a day? 5, so 12 in an hour, 12 times 24, 200, I don't know. Hundreds
Get my
something,
calculator.
right? Yeah. So you have in the hundreds timestamps per day. So when you look through the lens of that aggregation, you lose a lot of information because if you're expecting a trip to 0 as an inverter completely disconnected and stopped putting energy back into the grid, you would have to have that inverter disconnected for a certain amount of time for that to be picked up in a 5-minute by 5-minute timestamp time series. Whereas with the fault codes, what we've learned is that some OEMs, they do record fault codes on a second-by-second basis. So when we look through the lens of grid, over voltage, and under voltage, if I remember correctly, we could see inverters logging that particular fault a couple of seconds after the specific grid event happened. So going back to the event I've mentioned in Victoria, we know from IMO records that it happened at a specific timestamp. We could see inverters responding to that 1 or 2 seconds, sometimes 3 or 4 seconds after that particular event. Something that we would have lost if we're looking through the 5 minutes by 5-minute aggregation. So that by itself was a massive pool of information that we could draw from. The challenge was that each OEM would do things differently. So some OEMs would have specific fault codes that would be specific to inverter models. And some models would have 100 to 120 fault codes. a lot of these being string specific, but maybe 15 or 20 that were very useful to us for this particular project. And we could disaggregate exactly what the inverter was picking up. Grid over voltage or sustained over voltage or under frequency or anything like that. Sometimes fan alarms or current leakages and interesting fault codes like this. But some OEMs would have like a 5-minute kind of pulse signal saying that everything's okay or something's off, like literally a true or false flag. Some OEMs would only keep data for 3 months available to the public. They probably have that in their databases, but when querying the API, which is like the repository that you as a client can get the data from, you would only get 3 months worth of data. So the challenge here was really finding the OEMs that would give us enough information to work with the work package that we had, which was trying to identify if something happened with the grid. And that was super, super powerful, but there's still a lot of work to be done there. So I think the challenge is really standardizing the information you get from a lot of these different OEMs, but also making sense of their information. Some inverters would be registering up to, I think I got one with 8,000 fault codes in a single day.
Yeah.
So there is a lot of sifting through to be done through this information.
Yeah.
And that, I mean, we're discussing AI, for example, and machine learning, etc. We are always tempted to just kind of chunk that through an AI pipeline and see what happens. But I think there is a lot of understanding that has to be done with that information, because the thing about signals is that if you just get all of that information and convert into action, people will be overpowered about what to do. So I think when it comes to maintenance specifically, you have to be very careful with the decisions you make and what to do first, what to do second, what's going to give you the highest return on your investment. So I think there's a lot of thinking to be done behind understanding those fault codes before we are able to convert them into like a contextualization. And the other question you've asked is how much that was matched by the Diagnose algorithm pickup. I think we've tested with 32 fault codes, and what we found interesting is that they actually complement each other quite well. I think out of this 32, 28 or something like that's going to be coming out in the report we'll be publishing, but I think 28 out of the 32 were picked up by both systems, both processes. But then the fault codes would sometimes signify a grid over voltage or something that would require the inverter to trip that Diagno hadn't picked up yet. And I think that's because of the 5-minute aggregation. It was like such a quick trip that went back that when you aggregate 5 minutes, it's almost like a little bump that wouldn't be picked up as much. But also there was a few instances that Diagno would record a trip to 0 that wasn't logged as a fault, which I don't know what's behind it, but that's another very interesting thing to unpack as well. So at the end, we found that they complement each other quite well, especially because like 28 out of 32 were recorded simultaneously by both.
Mm-hmm. So again, maybe more research to be done, which is always good. We want to keep doing the research. I think I want to pick up on something that you said, which was there should be, what we're trying to do with all these work packages is really think through how to take an approach as opposed to just chunking it all in an AI and getting garbage in, garbage out. And I think at Diagno, what we're trying to do is try to find the signal amongst the noise in a way that really helps whoever the stakeholder is. Like you said, there's one inverter that produced 8,000 fault codes in a day. Those were probably accurate status signals from the inverter, but they're completely unhelpful to a stakeholder. And so with the work that you did here, and hopefully where we end up, we'll be able to elevate the right signal at the right time and suppress everything else so that a user stakeholder can actually take action if they need to, as opposed to just being like, I am being spammed by the inverter all day, every day. I'm going to ignore everything, which is what we're actually seeing happen. And there's a lot of beautiful dashboards out there that take those signals and sort of repackage them into a dashboard, and then they still let the user try to figure out what's going on. And they might be helpful to a certain extent, but that's not what we're trying to achieve. And I think each one of these work packages goes to the mission of Diagno, which is take everything that we've received, huge data sets, and boil it down to one kernel of truth that can be helpful to a stakeholder. In speaking about what can be helpful to a stakeholder, I just want to maybe challenge you a little bit, because I want to ask Fiac a question. With safety issues, one of the things that is required of, I think it's the 5033 that requires this in Australia, but an inverter must report a earth fault to the owner of the system. And they can do that by an earth fault alarm or an email or an SMS, which is great, and they do this, they're required to. But who's receiving that information and who knows what to do with it? So I wanted to see if I could ask you to remember how many earth faults we've detected over a given period.
Total number of earth fault detected, I think, if it's as a percentage I remember, I think it's around 1.2% or something like that.
2%.
1.2%. So it's let's say 1%, but we're talking about an earth fault now. So it's a very serious safety fire risk issue. And so even if it's 1 in 100 systems, that's still too much. That number should be 0, right? And to answer your other question, I'd be very curious to know how many system owners or system managers actually are aware of earth faults. Like we see over and over, because our clients are both owners or managers, well, one or the other. Sometimes they're both, and irrespectively of who they are, most of them don't know about it. And we were talking about the fault codes before, and it's kind of like, when your computer crashes and you get the blue screen of death, and then you get this giant log of like crazy errors coming out everywhere. It's, these errors are actually important for the technician, whoever's going to be here to understand what the issue is. But like, that's not going to be useful to anyone else. And like the inverter kind of does the same thing, that fault, that earth fault might be flagged somewhere in the portal, or it might be, but it's just going to be buried with like a number of other faults that are completely irrelevant, and so that's what we do here, picking up these very specific, important, relevant faults, triaging them. We have a very, very nice, sophisticated system that triages for us. It does 90% of the work, let's say. And then we also have the engineering expertise who looks at those triaged issues and then make a proper assessment, looking at these logs that the system owner, the system manager shouldn't care about, but we care about them. And looking at the data, looking at the outputs of what Bernardo and the team at UTS and at UNSW with Fiac have created for us. And just creating those very specific diagnostics for the system owner, which tells you what's the loss associated, what's the risk with this. So coming back to earth fault, this is obviously a very high risk issue. 2 days ago, we diagnosed an earth fault, and the client dispatched an electrician, and they found cracked panels all over the place. They had no idea, and I thought it was just another reminder of what we do is important. I remember for that site, if you were to look at the generation, you saw some generation loss in the morning. That's usually how they manifest, especially if it's the conditions are a bit humid. You get like a zero generation because the earth was actually kicking in, and then that would resolve throughout the day as the conditions get drier. But in terms of the generation loss, that wasn't actually that big. But the safety, the risk of this getting a lot worse was a lot more important than just the loss, the generation loss itself. So yeah, this was a huge win for us, and that's what we try to do, to pick up these very important issues and bringing them up to the attention of whoever cares about them.
Yeah, absolutely. Yeah, and like you said, the triaging is super important because not all earth faults are created equal.
Yep.
And some of these earth faults, and there's other mechanisms that can create this, but some of these earth faults can propagate over time to create a much bigger issue. And I guess that's where I was leading to with one of the work packages that you're actually still working on at the moment, was fire detection systems. And there are ways to detect arc faults in a PV system. The arc fault detection, usually you have a separate device or a specific type of inverter that can pick it up. But from 5-minute time series data, we found that there are anomalies that are present days to weeks and sometimes even months that precede a fire. Our sample set is admittedly small. But yeah, just hoping you could talk a little bit about the work that you're doing and where you think you can head with the work that you're doing. I think it's on work package 6.
Yeah, so I think there is the time series signal and there is the inverter code signal, right? And I think that's what we're using together. Now, the inverter code signal we already talked about. The problem is, there is two metrics we talk about. We talk about precision and recall. Precision is, if we have a positive error fault, how likely it is a true positive, right? And then we have another metric, recall. If we have an error, the false negative, right? So how should we detecting all the error fault? And so what manufacturers are doing is that they're optimizing for recall, right? They really don't want to have false negative, which makes sense when we talk about safety. But the problem is then, when you optimize for recall, so you just bring everything that's possible an error fault in there, is that you got a huge amount of noise signal, right? And that's where it comes to the boy who cries wolf, right? So you're managing this. The first error fault you're freaking out, and then you're going out and checking. But after the 10th one, you don't bother. You just flick it to the side, right? So it's a behavioral thing, right? Mm-hmm. So yes, the system indicates, but because there's so many false positive, you're losing that signal. So that's where we're trying to come in at UNSW, is that we need to bring context to this fault. And this context is coming from this time series. And when we bring those two things together, the error fault and what Bernardo, the excellent cook, has been doing at UTS, and the time series context, which is what you're talking about, these signals, together, I think that's where the magic can happen. We're still working on that, but you're looking at the current, the voltage, obviously the insulation resistance, and you're looking at the derivative of these, right? How they change over time, even the second derivative, right? And these are the features then that you use to engineer a system that takes fault code, takes time series, the derivative, second derivative together, and then makes a decision. And then, so for example, this system over the last 2 months that we've seen a degradation, and we've seen this voltage, delta voltage or delta current, maybe early in the morning. And based on previous knowledge, that this sort of could be a precursor, and we see the error code arriving on that day. Well, together, that's a trigger, right? So that's the sort of things we sort of engineering at the moment. I have to say, this is a challenging problem. Yes, in part because of statistics, in part because, of course, there's a lot of heterogeneity in the sort of faults that can happen in the systems, and there's a lot of heterogeneity in design quality, as you would know as well. But it's a very exciting thing because, a lot of our previous focus together has been performance, return on investment. But if your asset burns, your return on investment is zero or negative. So yes, I think that's going to be an important part going forward.
Yeah, I agree. I think that, like you said, maybe 1% of systems over, I don't know, a time period, maybe per year, will have an earth fault, and however many of them will result in a fire. So admittedly, the problem has like a low likelihood, but the consequence is super high. Like the Sydney Olympic Aquatic Center had a fire, I think, 2 years ago, and it made national headlines, and this is a black eye on the industry, but also the system is compromised, the facility is compromised. If we can avoid even a percentage of these, then this is a huge win, and it's simply a value add from Diagno. Like it's a feature that gets baked in. Again, coming back to the beginning of the conversation, a lot of things that we're working on here that has deep data science underpinnings boil up to a very simple takeaway for a stakeholder, which might only manifest very rarely, but super important. Yeah, I guess I'll set you up with a question for each of you. But over the last, let's call it decade, Australia in particular has just been building solar, building batteries, building wind, just build. And in my opinion, we're sort of turning a corner. The whole industry is maturing. You're seeing consolidation in the market. there's a lot of ancillary and peripheral services that are being offered or that need to be offered. So what I mean by that is it's not just installing solar anymore, or at least it won't be. It's home energy management systems, it's virtual power plants, it's the CSIP and controlling inverters from the network or from AEMO. That, like, the industry is becoming much more sophisticated and complicated, and we have to take everyone with us on that journey. So where I'm going to is, of the work that we've done under the Race 2030 project, what do you hope, maybe in some small part, what piece of that work do you hope will contribute to that journey that the whole market is going on, and eventually the whole world will go on?
Mm-hmm. Do you want to go first?
Anyone can take it first.
Well,
I
I
have
mean,
the same question for all
look,
of you.
The beauty of this is that there's accumulated knowledge, and then as the data set becomes bigger and bigger, the value stacks.
Mm-hmm.
So our first value was asset owners, right? And operators. And that's clear. But then, with the work you've been doing, Bernardo, is that, okay, well, the network, and then the DNSPs, and then, the, market operators, and then, so the value, there's different value stacks that you unlock. And I think that's extremely exciting, because not a lot of people are thinking about how a system is going to operate in 2050. But I think together we've been really starting to think about that. What does that look like? What is required? How can you predict production in 10 years? You can only predict that if you understand how a system will evolve. So I think that's one of the things I'm really excited about. And then obviously what we've been working on is really detection, diagnosis. But I think what we're going towards is really understanding how a state evolves over time. And I think not just a PV system, but PV plus BSS plus a grid, right? So really it's really going from, point in time detection to sort of evolution and understanding this evolution. But I'll let Bernardo sort of give their own take as well.
I think I want to kind of segue from that.
Yeah.
And I think what was really, really exciting and really beautiful about this particular project was to see the transition from understanding the problem from a asset owner or asset manager standpoint to a higher level of aggregation. And before working with energy systems, I actually worked in sanitation for a few years. And there are some cities out there that they use wastewater systems with sensors to understand things like drug abuse and antibiotic resistance, endemic diseases. So you can use those sensors almost to kind of pulse check on the health of a certain community. And I was asking myself, can we potentially do something similar or analogous with the information we get from inverters, almost like a hive mind? Can a council understand social and equity challenges from energy use? Can a council understand even, educational challenges from kids that might be correlation with energy use in some sense? So that it's really in its infancy, this idea in my mind, but I'm thinking if we start looking at the systems, not just from the asset owner or manager standpoint, but from other institutional stakeholders' standpoints, as councils or even nations in a sense, what kind of information can we get from looking through that lens? Not just from a financial standpoint. I think we've already been moving away from just that and thinking from a safety standpoint, health standpoint, environmental standpoint, but what other kind of signals can we get from that kind of integrated information when we connect all of these assets together? And not just PV systems from inverters, but batteries and vehicles, and then information from HEMS, like home energy management systems as well. So I'm really curious to see where that's going to take us.
I love that answer, and I love the phrase hive mind.
Yeah.
Well, that's a great point. Like, in a way, energy underpins sort of everything that we do. And if you can see, like, as an example with a council, what their what their solar production is, storage, and in a broader sense, what their consumption is, and then you can map that to other data sets, like socioeconomic, health, education, there could be correlations there that we didn't think existed, and then then you can do something with that. That's a great answer. Earl, let's see if you can match that.
That's how I go. Yeah, what do I go from there? I mean, to sort of echo what you guys said, like the value stack unlocking is really amazing, and it boils down to the richness of the data and how much data we're getting, and we're getting both, right? We're getting a lot of data, which is amazing, and going back to the asset owner, to sort of that level, I think the vision here is that we're trying, from a financial perspective, obviously installing renewable assets makes a lot of sense, right? You've got the battery-based program, and everything is solar, it's so cheap now. Batteries are getting cheaper, and then now it's EV chargers, and the next thing V2G is going to be huge as well. And so from that point of view, it obviously makes sense. But also, I think there's a general desire from people to be more independent. When you things like petrol, diesel prices going through the roof, people are affected by that, and trying to be more independent. And I see the way I see Diagno in the future is it's this sort of like renewable asset, clean tech companion kind of stuff. Like helping you being more independent. Keeping track of your assets, making sure that you get you make the most benefit of these amazing technologies that are coming up. At in a cost-effective way, kind of stuff. Maintaining those assets. How do you make sure that you get what you paid for? And so, yeah, the only way to get there is to to be able to provide some sophisticated again financial renewable companion that can tell you how to do things, how to maximize just sort of like your independence and stuff. Yeah.
Yeah, that's a great answer too. I guess for my part, I think that maybe Australia doesn't realize this, but we are a global leader in this space. Earlier you said this, I think about 40 gigawatts of solar in Australia for a population of just under 30 million. And Diagnose now is trying to get involved in the Philippines market, which is about a gigawatt for about 150 million people. This is a completely nascent solar market. And so all the work that we've done here as part of the Race 2030 project, but also as a country and both of your universities have done, I think there's a lot we can give back to the rest of the world. And so obviously we won't take it there with Diagno, but I think a lot of the research that we've done hopefully can be leveraged to help other countries as they go on this journey, because they will, 100% they will. They have to. It's just the way it's going. So I guess, do you want to do a whip around with closing remarks? Any further thoughts or ideas from the panel?
I think I just want to add to what you've mentioned about this collaboration and how you'll be entering a new market with, of course, a financial interest, but also I think you all have curiosity behind the challenge and engineering, technological curiosity in that sense. But I think what's important to mention as well is that all of the work actually we've done together is published and publicly available as well. We try to publish papers in which we map and make the algorithms all public and freely available as well. Of course, going from that to implementation, that's where the hard work is, but the information is out there, right? So we try to make it transparent and clear so other people can pick it up. Australia is a very unique market in itself, and of course going to new markets you're going to see the challenge, but I'm sure there's a lot of places out there that people could definitely benefit from that information in itself. So I think if anyone's interested, just looking it up on the Race for 2030 website, you'll probably be able to find whatever we've published up so far and whatever we're going to be publishing in the future. So I think just making sure that people know that this information is out there and available is quite important as well.
Yeah, I mean, for me, it's I totally agree with this, and happy that we were able to sort of publish and make this available. For me, I just wanted to come back on that scale, the scale of the problem. We have been so used to centralized thermal generation and managing this that we are still so far away from thinking how we manage in 2050 a system that's fully decentralized with many millions and millions and billions, maybe trillions of assets worldwide that are in households, on commercial sites, and the scale required for maintenance. So that's where I'm very excited to work with you guys and all of us together in how we can leverage sort of AI, Gen AI, agentic AI to really be able to meet the demands of this, because it's clear that just us doing it, even with all our automation currently, it's going to be a challenge to meet that growth. And I think agentic AI is coming at the right time, where we are able to sort of transfer some of the learnings that we have and to sort of start automating even more this to meet that demand, because I think otherwise it's a really difficult proposition.
Yep. That exact thought is the genesis of Diagno 3 years ago. One of the groups that we were working with owned about 800 solar systems.
Yeah.
And the way they were managing them was they would sort of circle off a few geographically co-located sites and send someone out to check them. And let's call it 60% of them would be completely fine. So waste of a truck roll. The other 40% would have some issue, and they'd require the inspector or O&M personnel to go back out another time, or maybe 2 more times. So just truck roll.
Teaching.
That's right. Yeah. So the O&M provider's happy.
Yeah.
But either the taxpayer or the system owner, whoever that might have been, not very happy. And you're absolutely right. In order to go from a centralized way of managing things to a fully distributed way of managing things, we have to be way more sophisticated. So yeah, bang on. Early on, have a closing thought?
Yeah. I thought maybe I'd talk about, but I don't want to say too much, obviously, but I can talk about some of the things that we're going to do next. We're well established in Australia. We've got a couple of sites in New Zealand. You mentioned we're trying to go into the Philippines. So this is one of our sort of next move, is to expand globally. We can do that obviously because at the end of the day we're a software as a service. There's no need for an additional hardware. We can just collect the data from the device cloud, and so it's very low friction onboarding, and it's very cheap as well. So that's something that we're obviously looking into doing. And you already sort of touched on that, but sort of thinking about this, agentic, AI perspective. How do we use all that rich data to better manage those assets, to come up with better diagnostics, to make us better at doing it, is obviously one of the pathways we're going to take as well. And we obviously, one of the big challenge for us is to support all the different device brands out there. So that's a major focus for us. We've onboarded a lot of the major inverter and battery brands on the market. So that's readily available now, and that's going to remain our strong focus moving forward.
Yeah, absolutely. This has been a journey for the inverter OEMs as well, and I think when we embarked on this, I didn't understand that, but now we understand the market is highly variable with regards to the approach that different OEMs take, the level of access you get to an API, different APIs for different OEMs, and how readily they engage with us. That's something that we have been working on. I don't know what percentage of our time we've dedicated to that, but it's something we've been working on for 3 years.
Yep.
And I think it's going to even take more effort going forward.
Yep.
I think we have a very clear idea of what we want to see the market look like when we interface with an OEM. So we're a little Diagno, but hopefully not too much longer. We can bring everyone along the journey. I guess for my closing statement, I just wanted to say that the Race 2030 has been amazing supporting us. When we've interacted with them, they've just given us lots of great feedback and lots of great support. And this has been a really important part of the Diagno journey, and it also allows us to work with 2 world-leading institutions with regards to machine learning and renewables, and allows us to work with you 2 fine gentlemen again. So
pleasure.
I guess that's my closing statement, and on to the next thing.
Let's do it.
Cheers. Yes.
Thanks, Chris.